really hot. So soldering stuffs, flux, magnifying glasses, microscopes, bus pirate. By the way, if you're using a magnifying glass to look, a physical one, to look at a chip, put some Rain-X on it, otherwise it's going to fog up like every 3 seconds and you're just going to be pissed. Yep.
Pro tip.
Yeah, pro tip, don't be pissed. Bus pirate, amazing little device. It is like the end-all be-all for raw bus analysis up to a certain hertz range. Debugging interfaces, great to have spare ones around. We'll talk about some of the mistakes here in a second that hardware manufacturers tend to make. And I don't know if you know this, but just desoldering the header doesn't protect your board from having a header put back on. So, pro tip. Yes, IDA Pro, we'll quasi-cover this. Quasi.
More in the slides on the disk.
Yeah, more in the slides on the disk. We'll talk about what you may be able to throw into IDA Pro that you would have gotten out of the chips that we're attacking. And then other stuff you might need, chemicals, respirator, balls, also dongs. You know who you are. So, security appliances. You know, what do we consider to be security appliances? I know a lot of people, when I ask them, you know, what do they think about security appliances, they think of firewalls, they think of IDS, they think of all these actual things that have been categorized as appliances and sold to you by vendors who want to charge you lots and lots of money. What we consider to be security appliances is basically anything that can be used to secure something. So some of the examples we'll be looking at is securing people from themselves, like a safe, or we'll be looking at something like securing your data, so the encryption system that we'll be demoing, well, talking about here at the end. So it can be practically anything that has some kind of security setting and is hardware related. The steps that we generally take, again, go consult a big massive deck of slides if you really want to break down all these steps, or find me in a bar and I'll be happy to talk to you for a price.
And there's an outline of a full methodology to do repeatable assessments on that slide deck as well. And again, we just don't have time to cover it because that takes 45 minutes by itself.
Yeah, pretty much. So, generally what you want to do is you want to define the goals. You know, what are you actually going after? Why are you attacking this device? You don't ever walk into something, especially when you're doing any kind of reverse engineering, and go, I'm just going to do this because it takes forever. Because you will sit there going, oh, I'll look at this now, and I'll look at this now. And at 9 months of work, you will have nothing but a pile of, oh, look at this now. So you want to define the device. And what we're talking about when we want to define the device is we want to look at it based on our goals. If our goals are to rip something out of the NAND flash, I don't have to sit there and mess with every other piece of that hardware to get that NAND flash. You know, I want to go directly to the bus. I want to do the stuff related directly to that chip. So when we're attacking something, we always have to keep the goal in mind as we define the parameters of the device and what hardware and what equipment we'll need to actually get that out. Gather all the open source information you possibly can. I know some of you may be decent social engineers, and if you ever talk to a sales guy, they just love to send you crap. The more you're like, I want to buy your piece of shit, they're like, here, have some documentation. Would you like chip specs? I've got some high-res x-ray photos too. Yeah, seriously. Like, I got stuff from one guy who was like, confidential company source information. I'm like, sweet, thanks.
No NDA, thanks.
Saves me from buying an electron microscope. It's in the budget, right?
Yeah. We're working on that.
Yeah, exactly. You know, examine the device for entry. Yeah. So, you know, a lot of these companies that create these secure appliances, especially ones that deal with key management, tend to have case sensors. They tend to have something to a magnetic sensor of some sort, or a light sensor, or it just happens to be to detect case opening, so that when you actually open the case, it theoretically dumps the keys.
Say bye-bye to your SRAM.
Yes, say bye-bye to your SRAM, yes. However, like the mistakes we'll be talking about here in a little bit, usually the implementation of those security mechanisms are terrible. It turns into a checklist. The security guy's like, I need case protection and key protection and all this stuff, and then the engineer's like, done. And we all know how well that goes. So, look at the best way in, look at the way that's going to be the least intrusive in the particular device, and then analyze the device circuitry networks and device components once you actually open the case, determine the most plausible attack vector for the actual hardware, and then attack like your life depended on it. Or go slowly, however you prefer.
Toro.
That would be tiger, 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 but
Oh, well, whichever. Attack.
So, common mistakes by the actual reverse engineers themselves. And I don't know how many times I have fallen victim to my own stupidity, and my friends as well, due to not taking copious amounts of notes and not taking pictures. Because when you're sitting in a pile of chips with a desoldered board in front of you going, I think it goes here, is not really the best time.
And orientation's always important, because if you hook them up upside down, they tend to let the magic smoke out.
Yeah. Powering up a board with a badly soldered chip just is a mess. Burning yourself with chemicals or fire, bad. Beer good, fire bad. See, I've taught you all something already. Not properly prepping for ESD, optical and magnetic isolation, if you need to work in an argon pressure environment, if you're dealing with nitrodized chips. Very, very important to have your test environment set up so that you're not actually going to ruin the thing that someone paid you or that you acquired to test yourself. Always take the time to make sure your environment's set up correctly and save yourself hours and hours of headache. And then my absolute favorite, get a backup device or a device of like make or something that's comparable to the chipset you're using, because once you let the magic smoke out of the thing you should be testing, you have pretty much failed. So you can't put it back in. It just doesn't work. And the list can continue ad nauseum based on the stupidity of the reverse engineer themselves. You know who you are. So, common mistakes by the people who sell you the really expensive appliances. Putting your case sensor wires right next to the vents. So, a paper clip and a pair of vampire clips, and I've just taken out your massively complex wire.
And that handy dandy heavy gauge steel case too.
Yeah, I love that. Speak.
And the heavy steel case too.
Yes, very impressive steel cases. And then you put vents in it. Hiding your chips under epoxy. Epoxy is not a security mechanism. For God's sakes. It really isn't. Like, you get this $30,000 piece of equipment with your security processor that holds your keys in it, and you're like, I'm just going to put epoxy on it. It's cool. Nobody can get to it. It's a bitch to get off. It's fine. Not using a built-in encryption protection mechanism on embedded processors, big fail. Not setting the read-write protect bits on the processor flash. There are fuses for a reason, and they're a real pain in the ass to get around. So if you set them, it'll only take me slightly more time and aggravation, but it's more time and aggravation. And if I get aggravated enough, I go find beer, and I stop working on your device. Not limiting access to debugging and provisioning ports. We're talking about the protection mechanisms for a desoldered JTAG port is not a actual protection mechanism. So if you're actually going to do that, think it out. Lock it down, use secure JTAG, use some kind of keying mechanism, use authentication where possible depending on your chipset to actually protect said device. And then my favorite, and Mark's favorite as well, running your I2C and SPI buses up to the user LCD, then back into your really hard case with all of your security mechanisms where it directly attaches to the boot flash bus. Because then you just take the panel off and you're on the bus.
And then you can rewrite your boot flash and maybe get some PXE action or a bunch of other stuff.
Yes. For those of you who would like to save me time, do that. And then, there's so many more attack vectors and mistakes we can go into based on the way the devices are actually engineered. but for the sake of brevity and possible beer later, I won't go into this. So, possible attack methods. There is voltage glitching, timing manipulation. You can Google these or go find that giant slide deck. Fuse resetting, if you can basically polish a chip in a clean room using a UV method, not for noobs. Just to warn you. Anytime you talk about chip shaving and nitronized chipsets and everything else, not a first time experience. Not good. The JTAG VDM provisioning interface debug, those are easily screwed up because most times they're made for debugging. So if you can get onto those and mess with it and twiddle some bits and do other very dirty sounding things to equipment, you have a good chance of actually causing it to spill its beans. And then debug path manipulation using the I2C switching flash pin mutex attacks, which he'll get into when we actually talk about the boards. So, the examples for the actual talk here. The thermostat in your secure hotel room. And you're like, why? Why does that thermostat matter? Well, most times these are actually tied into the central HVAC system. They're monitored. They're controlled by industrial control systems, which, in most times, due to human laziness, sits on the same network as someone's admin network or something else because, it's never true. It's never true. Hotel room safes. I love safes. I love electronic safes. They're the best. Encrypted storage device, which we're going to talk about here, and then Java cards, which we'll touch on because they relate directly to the encrypted storage device. So, the thermostat. We obtained a demonstration unit from some random hotel. It is an interesting device from this random hotel that has some really good prism-loving features. It has an occupancy sensor on it, an infrared programming capability, a bus interconnect, and the centralized monitoring configuration station we were talking about, and then the usual HVAC controls and relays and pushy buttons and display and what have you. So, I'm going to turn it into, Vanna White over here, and he will talk about the attack methods.
All right, I'm going to try to speak up so everybody can hear me. Is that good? Okay, good. So we're going to cover this thermostat. Hang on, there we go. Very, very quickly. So I'm going to look, if you look at the slides here, you can see that we've got a communications module that uses something that's somewhat like X10 protocol. If you've got automatic light switches at the house that you mess with using, the RF interface to the little box that sits into the wall and the power system, and it modulates signals on your power lines.
Don't eat it.
Yeah, I'm trying not to. So we also have, let's go from top down then. So we have the HVAC controls, and we also have network communications there, if you see that. There's a 5-pin interface, and I'm going to try to shoot this with a laser, but I'm not sure if I can hit it from here.
Fail.
Yeah, that's a big fail. Actually, I think the, oh, there we go. Okay. So up in here is where we're looking at right now. And we see that there's also an infrared module, which is used for, I would assume, programming this device as well. Didn't have time to do a full reverse engineer on it. And then you see the CPU here, which is a nice little 8-bit microcontroller. I believe it's I think it's actually the same as the safe, which is an ADC51 type instruction set. Different manufacturer though, so it's Philips. And an interesting note about this microcontroller is that it has a serial interface, an in-system programming interface, which is always on, can't be turned off from the look of things. And it's not hooked up to anything.